Okay. So we're very pleased indeed to welcome Jose Montesinos today, who's going to talk on crystallography and art. And so I hand it over to you, Jose.
So, and this talk is introductory in order to explain to people that, not theorists, that don't know much about orbifolds, and to explain what is an orbifold. An orbifold is like a manifold, but with singular points. A manifold is some sort of artifact that is able to produce a group and a simply connected manifold. The simply connected manifold is the universal covering. And the group is the group of covering transformations in the universal covering. So this is what is a manifold. It contains information. The information is twofold: universal covering and group of covering transformations. Now look the other way around. Start with a simply connected manifold in which some group acts. If the group acts freely, then the quotient space under the action is a manifold. But if the group do not act freely, has fixed points, then you need a new concept. That is the concept of orbifold. So an orbifold is the quotient of a simply connected manifold under the action of a group which has, in general, has fixed points. So the problem is to encode in some sort of artifact, which we call orbifold, to encode information so that the information encoded is able to produce the universal covering and the group acting with fixed points. So I will explain all these sort of things with examples coming from the Alhambra, the Alcázar de Sevilla. Here is the Alcázar de Sevilla, you see. There are so the group acting on the universal covering is related with tessellations, because a tessellation has a group of symmetries. The group of symmetry of a tessellation is the set of elements acting on this universal covering manifold, preserving the tessellation globally. There are spherical tessellations, in which case the universal covering is the sphere, the two-dimensional sphere, like this one. You can imagine that this is the two sphere, and it's a tessellation coming from a crystal of granite, called spessartina. There are these lines here, which are called striae. I don't know in English, but probably there you have the same word.
In English, striations.
Striations, thank you. There are striations. You see that there are reflections. For instance, there is a reflection around this great circle, sending this side to this side. And there is also a rotation here, fourfold rotation. So the group acting on this tessellation has fixed points. For instance, this is a fixed point of some element of the group. There are also Euclidean tessellations, like this one, coming from the Alcázar of Sevilla. Here the Moore letters, you see a knot here, you see? You see the figurine knot over here? Can you see it? I am putting the knot in the middle.
I can see it, Jose.
You can see it?
Oh, yeah, sure. Yeah.
That's the figurine knot. So I I didn't realize this, but in fact it's there. In the Alhambra of Granada, the figurine knot appears together with its mirror image, which is the same knot because it's amphichaeron. So this is the first table of knots that I know. So this is an Euclidean tessellation that also has a group of global symmetries. Now let us see what are the possible elements of the group that fix points. There are rotations. There's a five-fold rotation center. The notation for such a thing is the number 5. So if I take a point and I put the number 5, that means a five-fold rotation.
Jose, can I just say something? You seem to be wanting to admit it, but you are admitted.
I am?
Yeah.
I am what?
Oh, it doesn't matter. It's gone away. There was a signal that you've got two entries, but it doesn't matter.
I have 2 entries.
Yeah.
Let's see.
Doesn't matter.
I think just a second.
Todo está bien ahora.
Sí. Está bien ahora, pero now it's okay?
Yeah, it's fine actually.
Now it's fine. Here you see a center of five-fold rotation. They have 5 petals, but you see that the petals superimpose each other. Can you see that? No. This is on top of this, and this is on top of that, and so on. So this is a five-fold center of symmetry. There are no reflections. In the Alcázar de Sevilla, you have centers of rotation like this one. Observe here that this is over, and this is under. So this is some sort of link, no? I guess. It's a torus link. Now, an artifact that produces a three-fold center, that would be an orbifold. It's an artifact able to produce the Euclidean plane, the universal covering, together with the rotation of order 3. It's just a cone. You take a cone, you make the cone roll around, and then you put some painting here, and the painting get impressed in here in 3. This would be an angle of 2 pi over 3. But there are also centers of order in which the group acting on the point, fixing the point, is dihedral. It contains a rotation together with reflections. The notation in this case is 5 with a bar. The bar means or tends to suggest that there is a reflection. For instance, this flower here, this beautiful flower, it certainly has a rotation of order 5, but also there are reflections on these lines, these red lines. I don't know if you are able to see them, but in fact they are. And notice that in the center, in fact, there are only three pistilos in Spanish, estambres also, but I don't know in English. In the Alcázar, there are also centers of symmetry containing that are fixed by centers of by dihedral groups. You see the center of this hexagon, you see this star here. There are rotations, but there are also reflections. What an artifact, o sea, an orbifold producing a dihedral center of order 2, o sea, just a symmetry. Excuse me, somebody calling me. Sorry, is this. You see this butterfly? The butterfly, here is the line, and the notation is one with a bar. It's a mirror. In the Alhambra of Granada, you have this design, this tessellation with two parallel reflections, and they create this tessellation. Similarly, an angle formed by two mirrors, in this case, these mirrors, this is producing a center with a dihedral group of order 6. Now, but how to understand the global symmetries? For instance, this example coming from the Alcázar of Sevilla, which is very complicated, you see. One of the things that the Moors try to produce in the person looking at the tessellation was the idea of God. So something very difficult to understand. And they tend to occult, to make difficult to find the centers of symmetry. For instance, here there is a center of symmetry of order 3, of order 6, in fact, 1, 2, 3, 4, 5, 6. And this here is of order 2. But there are also centers of symmetry of order 3. Can you see any one of order 3? Just the center of this, we call it pajarita, birdie, pajarita. The center of this pajarita is of order 3, order 6, order 3, order 2. So the slogan is, what is a kaleidoscope? It's a fabric of symmetric designs. So a kaleidoscope is an orbifold. An orbifold with symmetry. An orbifold, sorry, with metric. A metrical orbifold having some Riemannian structure. If you abstract from the kaleidoscope the metric, and you consider only the differential structure underlying the kaleidoscope, then you get something similar to a differentiable manifold. You abstract all metric, and then you have a differential manifold, or a topological manifold, with singular points. And the information you need to add is the numbers 3, 4, or 3 bar, 4 bar, so on. With this information, you are able, with this kaleidoscope, with this structure, this orbifold, you are able to construct the universal covering and also the group acting there. This is one theorem of Thurston, which is the theorem of the developing map. There is a paper written by Yukio Matsumoto and myself proving this theorem of Thurston on the developing map. How a kaleidoscope produces the universal covering and the group. Now, let's see. The translations are the responsible of global symmetry. That's the main point. For instance, here we have a translation in one direction only. This is a note of 20,000 pesos, 20,000 pesos. But you see that the bottom of one note coincides with the top of of the other node. This happens with many nodes in different countries, especially in the old nodes of Italy and nodes in Turkey, and they are beautiful. In as much as the country is poorer, the nodes are better, more beautiful. But so you find that, for instance, there are some nodes in a country that I forgot the name. No sé si es something like Ossetia, or in which the nodes are extremely beautiful. But of course, the value is almost zero. Kaleidoscope causing a global translation is very difficult to imagine, but in fact is this. You see, this is the developing theorem. Now we are developing the kaleidoscope and producing the universal covering. And the transformation sending this red thing to this red thing is a translation. Now, a translation in two directions. When you have a translation in two directions, then the orbifold immediately becomes compact. There is no freedom, like in the case of the annulus. For instance, this is a node of Colombia also, 5,000. But you see that really it coincides, no? In the left side, in the top and the bottom, the very thing is very, very beautiful. And there are two translations. This gives a beautiful tessellation. And I hope that it's not obeying my order. I want to, okay, go. Yeah. In the back, you see the same. You see, this complicated design in the top and the bottom coincides with one. You cannot see the line of, perhaps here, you can see the line in which one node is touching the other node. Like in the Alhambra of Granada, this translation, these two translations produce a torus. So what is a kaleidoscope? Causing two translations. Of course, the torus. How to produce a torus? Like that. This is the torus. And now, how is the developing of the torus? How the torus develops itself and produces the universal covering, the Euclidean plane, and the group of covering transformations, which is generated by two independent translations. Now you see it going to the other side. Meridian and longitude are similar, equivalent. And now it is producing well, this program was made by a Portuguese girl, Cristina, many years ago, maybe 20 years ago. So it's not so perfect, but it's what I have. I don't have anything better. It's very nice, in fact, very nice. This is precisely what I mean when I say that the artifact contains information, universal covering, Euclidean plane, and the group of covering transformations, which is the fundamental group of the orbifold. By definition, an orbifold has a fundamental group also, which is precisely that group acting on the universal covering. It can be defined in the artifact directly without producing the universal covering. We can define the fundamental group by loops, adding some relations nearby the singular points. A kaleidoscope causing global symmetry without, perhaps this should be the letter F, without a reflection. We take a piece of paper and we make a triangle, any acute triangle like that. Yes. And then you see, you take the middle points, and then the angles are like that, no? These are similar. In fact, they are equal. A, B, C, so this is equal to that. So you can fold the triangle along this line, and along this line, and along this line, so that these three vertices come together. In fact, they come together. It's not so easy to see, but if you take any acute triangle and you do that construction at home, the three vertices will coincide and produce a tetrahedron. But this is not a regular tetrahedron. It's a tetrahedron such that the total angle in the vertices is 180 degrees. Is 180 degrees, A, B, and C. A, B, and C. So if you put some painting, in this tetrahedron, and you put the tetrahedron on the plane and start rolling the tetrahedron on the plane, it will produce some sort of tessellation. And since the angle here is 180 degrees, you will have 4 different centers of rotation of 180 degrees. See? Like this. Now look at the notes. The notes, you see, in this case, this note is rotated. See the moon is here and here. The amazing thing with this note, with this Colombian note, is that even if they are rotated, the pattern coincides. It's an amazing phenomenon. And now this tessellation has a center of order 2 here, in between these two figures here, center of order 2 here, which is different of that, and a center of order 2 here and here and here, which is the same, up to translation, and another one here. So it has 4 centers of rotation. If you take this pattern and then with a scissors you cut this thing, this triangle, and then you fold the triangle, you can make a tetrahedron, and then you roll the tetrahedron, and then you get rich, relatively rich, with millions of pounds, of pesos, no? sometimes the triangle is acute, but with a right angle. When the angle is right, then by folding this thing, you get a pillow with four corners. You see? A pillow with four corners is also an orbifold that gives patterns like that. Here is in the Generalife, in the Alhambra of Granada. I don't know if you can see, here is a center of rotation, is this, and this, and this is the same center. The ones in the vertices of the big triangle. But there are other centers like this one, and that one, and another one here. It's not very clear, the picture, but here is better. Well, forget about this red triangle, which is not well known. But you can see that there are four different centers of rotation of order 2. Here we have this swastika. Here is purple and brown, but here is purple and brown. They are different. And also, let's see, another one, this, look at this center. This corner. This is not the same as that. So in fact, there are four different centers of rotation. When I say different, I mean up to conjugation. So in the orbifold, all the centers which are conjugated up there are in the same orbit. Therefore, they produce just one point in the orbifold, in the quotient orbifold. This is an example coming from the Alhambra of Granada. And that comes from the Alcázar of Sevilla. It has the same symmetry as the one in the Generalife. There are no reflections, you can see, no? This is one center of order 2, another center of order 2 here. And I don't know, here is another center of order 2, you see? Here is, you have a torus like that, and you take the center of the torus and make a twofold rotation on the torus, you get 4 points of order 2. One is in the center and others are here. One here, another here, and also the corners of the torus. I'm trying that this program obeys my order, but it doesn't. The theorem of developing something means that when you are developing along a path and the path crosses itself, as is going to happen now, very soon you will see that it crosses itself. Then you have to prove that the figure in the crossing point coincide. Otherwise, you see now, you have to prove that. So we have developed our orbifold along a path. And then you get a symmetric design on the universal covering. Now, how to understand this? Well, the classical Euler characteristic, which in case of the tetrahedron and the cube, etc., is 2, number of vertices minus edges plus faces, has to be generalized in the following way. No. I. Yeah. What is the Euler characteristic of a kaleidoscope? You have to weight the vertices. The weight of a vertex is not one. It's one over the order of the group fixing the point. For instance, if you have a point marked 2, the weight is 1/2. It doesn't weight like 1. It weights 1/2, 1/2. So then the Euler characteristic is the Euler characteristic of the sphere, which is 2 minus 4 points, minus 4, plus 4 times 1/2. 2 minus 4 plus 4 times 1/2 is 0. And why is this? Why is the Euler characteristic 0? Because this orbifold has an orbifold covering. An orbifold covering is like a covering. In the theory of manifolds, you have coverings between manifolds. Here we have coverings between orbifolds. And they are the same idea. So the Euler characteristic is multiplied by the grade, by the degree of the covering. But this orbifold is covered by the torus. As I said before, if I have a torus and I take the center of the torus and I make a 180-degree rotation around the center, what you get is this orbifold. So since every Euclidean orbifold is covered by the torus, the Euler characteristic of the orbifold is 0. So to obtain all the groups of symmetries of the Euclidean plane, the crystallographic groups of the Euclidean plane, what you have to do is to find all the orbifolds with Euler characteristic 0. The fundamental theorem is this: the Euler characteristic of a Euclidean kaleidoscope is 0. And this is the key to obtain all of them, 17, up to homeomorphism. Then you have to check that the topological classification equals to the affine classification. This is it's a little more difficult to explain now. So for instance, you have the sphere with 3 singular points with orders m and p. The Euler characteristic is -1, is this precisely. And the only solutions are 236, 244, and 333. So if the kaleidoscope has underlying manifold the sphere, the 2-dimensional sphere, and you have 3 singular points, the only possibilities are 236, 244, and 333. If the number of points is bigger than 4, it's impossible to obtain the characteristic of Euler 0. If the number of points is 4, it's possible, but the 4 points have to be 2, 2, 2, 2. From 2 to 2 to 2, 2. From 2 to 2. But see, here is 2, 3, 6. Topologically speaking, is like that. An orbifold, topologically speaking, with no metric at all, is just the 2-dimensional sphere in which you have marked 3 points, and then in these 3 points, the new information is 3 numbers, 2, 3, and 6. That is the orbifold. But this orbifold might be geometric. And then to understand its geometry, you have to compute its Euler characteristic. In this case, it's 0. So in fact, it must exist by a theorem of Thurston. It must exist an orbifold which is Euclidean with these singular points of order 2, 3, and 6. In fact, it's just the double of a triangle. of angles pi 2, pi over 3, and pi over 6. You make the double of the triangle. So it's a pillow with 3 corners. And the orbifold is here. It develops. You see that it's a triangle, but the top of the triangle is pink and the bottom is green. In one side is green and in the other side is pink. And then you start developing the triangle, just doing that. This is a developing map. The amazing thing that this thing works also for hyperbolic orbifolds in any dimension. In the case of 3-dimensional orbifolds, the singular set is a graph, many times it's a knot or a link. And then you have to put some information in the knot or in the link, which is a number, an integer. For instance, the trefoil together with the number 3 is an spherical orbifold. What means that there is a threefold covering space. Well, that the universal covering is that 3-dimensional sphere. Now let's go to. Here is a tessellation in the Alhambra of Granada, which is governed by this orbifold. This is of order 6, of order 2 between these two things, and of order 3. It looks like of order 6 by the star, but in fact you have these 3 corners. This is one of the most beautiful examples that I know. It's from the 14th century. The Alhambra of Granada is almost all what you see there is 14th century, 13, 14. But there are things from the 10 and 11 and 12th century also. This is just beautiful. Here is another example. This is also of order 6. In between these 3 things, this is also of order 3, and that is of order 2, in between these 2 things. This design of this tessellation appears also in the Alhambra. Here is an example. You see the center of this star is of order 6. And in between these 2 stars, you have the center of order 2 here. And here, precisely in the very center of these 3 stars, is the center of order 3. And there are no symmetries. By the way, this aside tessellation has also interesting symmetry that we will see after. Another example that I explained at the beginning is very beautiful. This is from the Alcázar de Sevilla. Another case is 2-4-4, corresponding to this typical equilateral isosceles triangle of which is with an angle of 90 degrees. It's a pillow with 3 corners. Here is the same. One side of the triangle is pink, and the other side is green, so that in fact is a pillow. Well, it doesn't obey my order, so. An example from the Generalife. Yeah. There are, is S244, so it means that there are 2 different centers of order 4, not conjugated. One is in the center of a black circle, and the other is the center of a blue circle. And here is a center of order 2. This is in Generalife. Another case, 2 centers of order 4, one here. and a center of order 2 is not so easy to. Here is another center of order 4. This is swastika here. You see? 4 and 4 different. And the center of order 2 is here. Sometimes it's not so easy to find. In this particular case, it's very difficult to find the centers of order 2, 4, and 4. It took me at least 20 minutes to figure out where are the centers, because you see, it's not so clear. You see, this center here seems look similar to that, because locally it's the same, but not globally. You see there are 4, 8, and here only 2. So this center of order 4 and these are different. And in fact, this is not of order 4. Oh, it is. Yes, it is. It's of order 4. And where is the center of order 2? Here? No. Where is the one of order 2? It took me 20 minutes to figure out where it is. It's not so easy. This is what the Moors tried to make. Very difficult to understand the symmetry, because they thought that God was infinite in 2 directions, and also the difficulty of understanding came from the complication of the pattern. That is very difficult to understand. Here is the solution 333. It's an equilateral triangle with a double. Here is the let's see if now reacts. React. You see, it's pink in one side and green in the other side. It's a double of a triangle. And now it develops. The pink part so far it's only the local center. Now it becomes global. One center of order 3 and another here. This comes from the Alhambra of Granada. This is one center of order 3, another of order 3, and another of order 3. Different. No reflections. The same design. That comes from the Alcázar de Sevilla. It's the same design. Now, each one of these orbifolds is a covering, is a twofold covering. For instance, you get this orbifold, and you take this plane of symmetry, and then the top and the bottom are related. This is an example of an orbifold covering. This covers this 1, 2 to 1. The point in the north and in the south go to this point here. But now the angles, the 2, 3, and 6 centers of symmetry of order 2, cyclic of order 2, 3, and 6 are converted in points of dihedral symmetry, because now there is a mirror. Roger Fenn, who is this fellow here? You are not Roger Fenn. Who is? You are not that. It's a transformation. So S236 is a twofold covering of D2 bar, 3 bar, 6 bar. So in fact, this is the triangle itself, the triangle itself with the sides of the triangles are now mirrors. I don't put here the symbol 1 bar, but I should put here the symbol 1 bar, meaning that this is a symmetry. Every point in this side has symmetry dihedral of order 2. This is the triangle. Now, one side and the other side have the same color, pink. And then that produces the reflections, you see. The best example that I know is this one in the patio of Arrayanes in the Alhambra of Granada. You can see, if you look at this picture with your eyes half closed, you will see that it's made of circles. Roger, if you look at this picture with your eyes half closed, you see that it's made of circles. This window is in the patio of Arrayanes, but it's inside some sort of closet, lateral closet. And you can, in fact, you cannot see it except by taking a ladder. And when I was at the Alhambra in the year 1987, making photographs, I found this example in the patio of Arrayanes. And the man that made the photographs for me, at the time there were no cameras, no digital cameras. He had to take a ladder and make this picture. And this, according to how is it called this in English? The curators, no? The curators of the museum, curator or curator? No, I cannot hear you.
Curator.
Curator. The curator said to me that this is the 14th century original. And there is only one window. Is this one. Here is developed the window. You see that it's made of circles. It has axis of symmetry. In fact, order 6, order 3. It looks order 6, but it's over 3, you see. And then each one is a covering of another one. I will go now a little bit faster. This is the same triangle with mirrors. Here is an example from the Tower of Damas, which is close to the public. You cannot see that. You will never see that. It's in the Tower of the Damas. It's a beautiful design, in my opinion. Here it is. This has been done by my student and colleague, Antonio Costa. But now, and this is an important point, there is a covering of this orbifold which is different from the one that I considered before. You take the point 4 and the point 4 north and south, then the involution, reflection on the equator, produces this thing. This is a cone point of order 4, and this is a dihedral point. You see? So this is D, disk, S, sphere, D is disk, 4, 2 bar. So what you will expect? You will expect a tessellation in which there is only one center of order 4 and centers of order 2 through which mirrors pass. Well, the artifact that produces such a thing is this. This is the center of order 4, and in the boundary, there is a corner of order 2, which is an angle of 90 degrees. Well, I will put this, it's becoming late. Let's see how it develops. This is an idea of Cristina, this Portuguese lady. Now it must be a lady. At that time, 20 years ago, was student of Arala Chavez, professor at Coimbra University, or at Lisboa. I don't know. No, professor at Porto University. Now it's producing the fourfold center of symmetry. A center of symmetry which is cyclic of order 4 without mirrors, which is exactly in the apex of the cone. Hey, yeah, it's very slow, you see. And this corner here, that's the one that will produce the 2 bar center of symmetry, which is dihedral of order 4. We are closing the it's not working properly. I have Linux, and Linux is not good for this. Now look what is happening now. It turns around, you see. It is it's like taking my shirt up. You see? It's an amazing thing. And now we can complete the point of symmetry dihedral of order 4. It's very slow because it's very old program. Now, you see? And at the same time that is producing this center of order 4, also is producing here a dihedral point of order 4. Well, I think you got the idea. There are many examples in the Alhambra with this design, with this hash column, but this is so beautiful, also 14th century. Center of order 4 with no mirrors. Center of order 2 with 2 mirrors. You see? This is copyright of my student Antonio Costa. Another example of the same thing. Center of order 4 with it like a swastika here, and then center of order 2 with mirrors. Same thing, 3, 3, 3 gives 3 bar, 3 bar, 3 bar, which is the triangle, equilateral triangle with mirror. This is the kaleidoscope that you find in shops for children, that you look through a tube. This is the one. But this is very badly represented in the Alhambra. The one that should be more represented, because it's the one that we have seen since we were children, is the one that is not represented in Alhambra, except for one example, which is very, very, very poor. In fact, is in this Patio de los Leones, there is a chamber which is called Sala de Abencerrajes. In the Sala de Abencerrajes, if you see the Patio de Leones, there is the mucarna of the ark. The ark is like that, no? And it produces some, is inscribed in some, is the ark, and the mucarna is this triangle. This is called mucarna. And in the Mukarna, you have triangles, which are black and white. This design has 3 bars, 3 bars, 3 bars, and there is no other one that I know in the Alhambra. To say that there is no one in the Alhambra is a very dangerous proposition, you know, because there are literally thousands. And this is the mistake that what was a man in a very wonderful mathematician in California, I guess, that he claimed that he couldn't find the 17 groups in the Alhambra, and he claimed that they didn't exist. And that was, I read that thing in 1977 or something, and I say, this man doesn't know what he's saying. There are literally thousands of these designs. So I went to a set of photographs, and I found 16 in photographs, but not the 17. I didn't find that. And then I went to Granada, and I was looking there, and one friend of mine said, no, there exists this thing in the Sala de Abencerrajes. He knew. And there is a copy made by some architect in the 19th century. There is a copy in the museum of some tessellation that it is lost, and in fact is governed by this design. So in fact, it has existed. But, see, that's in the Mukarna. That's the design. It's very trivial. But the amazing thing is, this is the one that is produced by the ordinary kaleidoscope. It should be thousands of these pictures, but there are not. There is only one. So in fact, they didn't know. This is a silla. Silla is a chair. Chair in the museum. You see the triangles. Of course, it's a equilateral triangle. And then it comes this. The pillow with 4 corners has 4 different orbifold coverings. One is cutting the pillow by half, and then that produces tessellations like this, which is one center of order 2, another of order 2, 4 centers of order 2, and symmetries. This is very common, like that, or like that. But it has there are other possibilities. The two twos are on top, and these 2 twos are on the bottom, and then there's the reflection. That produces a disc with 2 centers of order 2, with no mirrors. Let's find an example. So that is the quotient space. That is one example. It's a zigzag. You see, the center of order 2 is in the center of this rondo, of this white, or in this blue. And in fact, there is a mirror, but the mirror is not passing by any center of symmetry. Another example, in the Alcázar de Sevilla, you see, these zigzags. And then you have another which is wonderful. You take the antipodal transformation in the sphere, which gives as quotient space is the projective plane. And these 2 points are identified with these 2 points, and then you get the projective plane with 2 singular points of order 2. The underlying manifold, in the technical way of saying this, is the underlying manifold is the projective plane. And the kaleidoscope is a non-orientable kaleidoscope, because it contains orientation reversing symmetry, which is the antipodal map. And it has 2 points, 2 cone points with no mirrors. This one is here. In la puerta del vino, the door of wine, the Moors didn't drink wine, you know, well, at least in public. But there is the so-called puerta del vino. I don't know why. Now look, this tile and this tile are like that. I am like that. Can you see?
Yes.
That comes from the antipodal map. Has no fixed points. This has fixed points, you see. But it does not. In the universal covering, which is the sphere, which is the plane, in the twofold covering, orbifold covering, which is the sphere, then that corresponds to the antipodal map. It reverses the orientation. And the centers of symmetry of order 2 are in the center of this tile and in the intersection of these two tiles. Here is a center of order 2 and another. And another example is in the mucarna of the Puerta de la Justicia. You see, this has to be done at a distance of 20 meters. It's very high. This is a big puerta, difficult to find. This is one of the examples that this mathematician in California couldn't find, but in fact it's there. This comes from the Roman times. It's called, in Spanish, it's called espina de pez, fishbone. It's called fishbone. So I said that the pillow with 4 corners have 4 different coverings. Another one is this, norte, sur, and these are in the mirror image. So in the quotient you have 1 center of order 2 without mirrors and 2 centers of order 2 with mirrors. Let's see if this is possible. One center of order 2 without mirrors. Here. A center of order 2 with mirrors. And a center of order 2 with mirrors. In the center of the black bone and in the center of the white bone, you have centers of order 2 with mirrors. But in between, here is a center of order 2 without mirrors. So the theory of orbifold coverings gives an enormous insight on this topic. Well, let's continue. Well, we forgot the case of the Mobius band. The Mobius band has a twofold covering, which is the torus. The center of the Mobius band produces this thing. You see? You will see immediately. This is very beautiful. Eh? It produces this. Now you see that this narrow part is repeated here, but at the right side. Go, go. Ah. Ah. You see that this narrow part is now here. So you can do that with Möbius band produces this glide reflection, is producing a glide reflection. But that if you take the Möbius band and you plug a disk, you get a projective plane. So in fact, that corresponds to the antipodal map, as we have seen before. An example of this in the Alhambra of Granada is that this is the Möbius band. Why is the Möbius band? Because you see that these two are related by reflection. The line of reflection is this. So it's like if the Möbius band was covering this part. Up, down, up, down, up, down, up, down, up, down, up, down, up, down. And the boundary of the Möbius band is that, which is just an ordinary mirror. But in between these two mirrors is this line, which is the middle part of the Möbius band, producing up and down, up and down. You can see the Möbius band running like that. And the Möbius band reflecting itself, producing the different parallel bands. Here it is. It's an example for the Alcázar de Sevilla. And of course, there is the Klein bottle, Euclidean, appears in the Puerta del Vino and also in the Oratorio del Parral in El Generalife. It's not easy to see, but a Klein bottle contains a translation and a glide reflection. The translation is this, and there are glide reflections. Glide reflection in this direction and translation in the horizontal direction. The complication here, these complications, sometimes reduce the symmetry to the one of a torus, but not in this case. And finally, you have the symmetry of the torus that we have seen before. You see, the complication of the design makes the symmetry very poor. There are only translations, nothing else. So I thank Antonio Fernández Puertas y Pura Marineto. These are the directors, the curators of the Museum of the Alhambra of Granada in 1987. Both are now retired. Deborah Tejada is a Colombian lady. Arala Chavez and Cristina Lopez, they make these beautiful developing maps. And Antonio Costa made these sort of things. Guardar. Yeah. Well, I like to open another. Well, it's already very late, isn't it, Roger?
Maybe save it for the next talk. But
oh, what is all this?
I don't know.
It has been.
References, are they?
I don't know what it is. That is something that I like to talk someday.
Wonderful.
Can I email you a question?
Can you?
For how do I do that? I have a.
Ask it now.
Who is talking?
I'm Tony Robin, and I have a picture from Alcazar
De Sevilla.
in Sevilla, and you showed it in one form, and I have it in a slightly different form. And the question is, what is the cone? The difference in the cone? It doesn't have and you showed it with squares, and I have it with rectangles, and the stars in the middle are not 8-pointed stars, but they're 6-pointed stars. And
okay. Just send me the picture to my email.
Okay.
My email is very easy to do. Is Montesin.
Well,
You drop OS.
And I will forward it.
Okay. Thank you, Roger.
Okay. So.
But next talk, I want to talk about, but I don't know how to do that.
Mhm.
But you will be able to.
What did you see now?
Variedad
Abiertas
abiertas y cubiertas ramificadas.
like that.
Sí.
This I would like to talk sometime. The talk is already prepared, you know.
Mhm.
It's proving that any three open manifold, three-dimensional open manifold is a branch covering of the three-dimensional sphere minus a subset of a Cantor set, a Tain Cantor set is the proof of that. And also there are these beautiful things. This, for instance, this is a knot. This is a string. As a matter of fact, it's string. It's a while knot the while knot is at infinity. And the 2-fold branch. This thing has a 3-fold branch covering associated, which is the three-dimensional sphere. So the three-dimensional sphere is a 3-fold branch covering of the three-dimensional sphere. And the branching set is this wide knot, which is called Fox knot. It was the topic of a paper by Fox called A Remarkable Knotted Curve in Annals of Mathematics. And it has a 3-fold covering associated to it, which is S3. And that one corresponds to Whitehead manifold, open 3 manifold. Then I want to talk someday about the consequences of this theorem, that the open 3 manifold defined by Whitehead is a 2-fold branch covering of the 3-dimensional sphere. And the branching set is string, is this string. And then I have to talk about the relationship between while knots and compacta. This is the so-called snake-like compactum of Bing with one end point. The end point is just this O here. And the compactum goes like that. It's a compactum. It turns out to be that I can produce the so-called contractible, you know, that the weighted manifold, the open 3-dimensional weighted manifold can be embedded in S3. And the complement of the embedding is a compactum, which is not simply connected, which in fact I can depict this compactum. And is here depicted somewhere. Here. Here is depicted. This is the compactum, so that its complement is the Whitehead manifold. I can depict the compactum. It's made of two copies of the snake continual being, but they are linked together. So in fact, the theory of stains of wild knots with one wild point at infinity is equivalent to studying some compacta. And this is something that is in one of my papers, but nobody has continued this investigation. It's just it's the start of a deep investigation. It's the starting point, you see. Here is another example of same sort of thing, no? This is the end point of the compactum. This corresponds to the Whitehead manifold. But I have to fill up details, put some text in the conference, so I cannot talk about that right now.
Sure.
Well, that's
So what is your schedule, Jose, for giving us further talks?
Well, my schedule should be to give me time. I am very old man.
we're all old men.
We are very old, and then I cannot work. My knee, for instance, is hurting me enormously. Yesterday, I don't know what happened, and I have to go to the doctor. And it takes a lot of time. And to put these things written down in this way takes me a lot of time. I would prefer to go to a blackboard and explain in the blackboard, no?
Mm-hmm.
I cannot do that. And I need time. So I would like to talk about, but I cannot find it here. Let me. Well, I would like to talk perhaps in 10 days or in 15 days.
Let me suggest,
Okay,
Jose,
so 2 weeks from now. Yeah,
Right,
2 weeks
right.
from now.
very good.
And Lou will speak next week on this, on the things I've forgotten what. But if Lou speaks next week.
Okay, so I'll talk next week about quantum field theory and Vasiliev invariant.
Who will talk next week?
Luke Kaufman.
Luke Kaufman.
Yeah.
Wonderful.
And maybe in a fortnight's time, Jose, you will be ready to speak.
Yeah, in 15 days. Because the talk is already prepared.
Jose, this was a wonderful talk. Do you have a collection of the slideshows that you have that you would like to give to us? Because if you send them to us or give me a drop site for it, I will put it in our Dropbox so that we can all look at them.
Who is talking?
Lou Kaufman.
Lou. Lou, how are you?
Fine.
I cannot see you here by some reason. No, certainly, Lou, I will send to you these talks. They are in PowerPoint, and also a number of papers. I have to give a number of talks in Spain, and and there are like 5 or 6 talks. I will send to you right now.
Great.
You can do whatever you want to do with And
Okay.
it's a great pleasure to listen to you, Lou. Great. Why I cannot see you?
I don't know.
We've
I
got-
see
Maybe
you.
you stop sharing the screen.
You need to yeah, unshare perhaps.
You are screen sharing participants, 11 participants. Ah,
It was at one stage 17, like the number of.
but here is people. I can see the Roger Colin Rook. Hello, Lou Scott Carter, James Montaldi. I don't know. Ken Perko.
So
Maritania,
You-
Paolo Cavicchioli. Wow, yeah.
if you can stop sharing the screen, you can switch to a gallery view.
Ah, stop share. Right.
There we go.
Ah, Lou, can you? Great. And okay, so Lou, I will send to you right now when I stop this thing. In 15
Great.
days, I will be prepared to talk more. So the idea is to give to people which is not theory some idea what is an orbifold. This is what the idea. But next talk will be more specific.
Okay, so well, I want to thank you very much, Jose, for such a beautiful talk.
And
Look forward to hearing you in a fortnight's time.
Colin, how are you?
Okay, how about you?
Fine. I have used your car.
Have
Your
you?
car has been running through National One from Madrid to the mountains. And I remember one very close curve done by Roger. It was a rover, I guess.
Yeah.
Yeah.
It was a rover.
This is a long story, which perhaps will.
Well, anyway,
For another
let's okay, goodbye then.
Okay, so there are lots of questions and things, but maybe we'll save them up for.
No, if somebody wants to ask questions.
So I think we should perhaps stop now. So thank you again, Jose.
Okay, goodbye.
We'll see you soon.
Maritania, how are you?
Hola, hi.
Sí. Where are you now?
Now I am at Providence, at the US.
Good Lord.
Yeah.
Una viajera incansable.
Sí, ahora que siendo joven parece que uno tiene fuerza de moverse mucho. Ahora
Sí.
toca un poco eso.
Es lo que hay que hacer. Bueno, pues nada, adiós entonces.
Venga,
Adiós.
bye.
Goodbye. ¿Cómo se cierra esto? Ahí.